Hello, and welcome. Today we're taking on a tough Olympiad problem, but don't worry, I'll guide you through it clearly and step by step. So we have a right triangle, hypotenuse measures 10 inches, and the altitude drawn to this hypotenuse is said to be 6 inches. Our job is to find the area of the triangle. Before jumping into the calculations, let's pause for a moment and see where this problem comes from. It was posed by the legendary Russian mathematician Vladimir Arnold, who loved using it to playfully challenge his American students. Interestingly, school kids in the US could solve this puzzle without much trouble. But when Moscow students tried it, they struggled. Why was that? Now, who was Arnold? At the age of just 19, he cracked Hilbert's 13th problem, something many thought was impossible. Later, he went on to create entirely new areas of mathematics: topological Galois theory, symplectic topology, and CAM theory. Yet despite being a genius, Arnold had a gift for teaching and making math exciting. This puzzle actually appeared in one of his handbooks for children, ages 5 to 15. Let's go over how American students solved the problem. We have a right triangle with a hypotenuse of 10 inches. Upon the hypotenuse, an altitude of 6 inches is dropped. So, what's the area of the triangle? Let me just rotate this diagram so that it matches the ones shown in textbooks. We have a triangle, and we have two dimensions. We know the area of a triangle is equal to 1/2 times its base times its height. So, we have a horizontal length of 10, which we'll take as the base b, and we have a vertical height of 6, which we'll take as the height h. Now, we just substitute into the formula. Area equals 1/2 times 10 times 6. So 10 times 6 is 60. Divide by 2, and we get 30 square inches. And that's the answer American students gave. The only problem is this. If you just go through that rote calculation, it's not the correct answer. Let's try to understand. Imagine we have a base of 10 inches. Suppose we draw a perpendicular to this base that's 6 inches long. Now, what happens if we complete a triangle with these 3 vertices? Will the angle at the top be 90 degrees? It doesn't look like it. What if we move it over? Still not 90 degrees. What if we move it again? Still not 90 degrees. Are we ever going to get a right triangle with these dimensions? The answer is no. Let me reset the diagram and show you why. We have a base of 10. Suppose we let this leg be equal to x. That's one portion of the hypotenuse. The remainder must add up with this leg to make 10, so the other part is 10 minus x. Now, inside this large triangle, we have 2 smaller triangles. One has legs 6 and x. If we rotate it, we see it's similar to the other triangle inside the large one. That gives us a proportion. 6 by 2 equal 10 minus x by 6. By cross multiplication, we get this. So, 6 multiply 6 equal 36 equal 10x minus x squared. By rearranging it, we get x squared minus 10x plus 36. Oh look, this is a quadratic form. We use the quadratic formula. X equal 10 plus minus square root of 10 squared minus 4 into 36 divided by 2. Then become x equal 10 plus minus square, this 10 square become 100, and that become 144 divided by 2. By simplification, it equal 10 plus minus square root minus 44. Divided by 2, we can write this 44 as minus 4 times 11. By simplification, it become x equal 5 plus minus iota, or I square root of 11. But what does that mean for the original diagram? X was supposed to be a positive real number, and we ended up with a complex number. This is physically impossible in geometry. A triangle cannot have these dimensions. But what does that mean for the original diagram? x was supposed to be a positive real number, and we ended up with a complex number. This is physically impossible in geometry. A triangle cannot have these dimensions. The Russian students didn't think about it algebraically. They immediately saw that it was impossible for geometric reasons.
Let me quickly review something important. Suppose we have a right triangle ABC. We want to show that the circumcenter of a right triangle is the midpoint of its hypotenuse. First, construct the circumcircle that passes through the three vertices. Let's call the center O. To prove O is the midpoint of AB, we need to show that OA equal OB. And since O is the center of the circle, OA, OB, and OC are all radii, so they must all be equal. How do we show this? Start with the right triangle and construct the perpendicular bisector of AC. It bisects AC, so the two parts are equal. Let's call that midpoint D. This perpendicular bisector crosses AB at a point we'll call O. Because DO is the perpendicular bisector of AC, every point on it is equidistant from A and C. That means O is equidistant from A and C. Now, look at the triangle ADO. If we scale it up, it's similar to the larger triangle ACB. The similarity ratio is 1:2, since AD divided AC equal 1:2. So AO divided AB equal 1:2, which means AO equal OB. Therefore, OA equal OB. And since we also have OA equal OC, all three are equal. That proves O is the circumcenter of triangle ABC and the midpoint of the hypotenuse. But how does this help us? Let's go to a right triangle with a hypotenuse equal 10. We will construct the circumcircle. We know that the center of the circle is at the midpoint of the hypotenuse. So we know that if this point is O, we can calculate the radius will be half the length of the hypotenuse. It will be equal to 5. So that will be the same length for this vertical radius. Now, any altitude of this right triangle will be a vertical distance that's parallel to this vertical radius. And we can easily see visually that any height h must be less than or equal to 5. You can't have an altitude to the hypotenuse of a right triangle that's larger than half the length of the hypotenuse. Therefore, a value that h is 6 is impossible. And that's the key lesson here. You must think about the problem before you calculate. This reminds me of a famous, though probably spurious, quote attributed to Albert Einstein. I would spend 55 minutes defining the problem and then 5 minutes solving it. Unfortunately, in today's testing, students often only get 5 minutes to solve a problem, leaving no time to define, no time to think. That's why it's wonderful we have YouTube, where we can explore problems that make you think and reveal the joy of mathematics. I hope you find it helpful and enjoy it. If you did, please give this video a like and subscribe our channel for more problem-solving strategies. Thanks for watching, and see you in the next one. Good luck!